topic for today's discussion is molecular orbital theory from chemical bonding chapter. So if you see that particular chapter contains a high weightage, it's going to be important with regard to your higher studies, your board exams or your competitive exams, and in that particularly you have a topic called molecular orbital theory that comes at the end of the chapter, right? That topic is going to be importantly treated today. We shall learn some short tricks, we shall learn some implications of the molecular orbital theory, all with a very good understanding. Come on, let's give it a shot. So I have here presented some of the orbitals on the board. So as you can see, I have drawn S, P, D orbitals. F orbital we don't need for our school level. Then you know that there are also orbitals other than F. Like you can go on in alphabetical order, like S, P, D, F, and then you can say G, H, I, J. So now you can keep going this way, okay? So now what are orbitals? Orbitals are considered to be the home of electrons. You know, electrons need some place to reside in. They keep moving, that's true, of course. They move three-dimensionally, that is, they can move in all ways. If you let them here in this room, they are going to move everywhere around. So, but there is a particular pattern in their movement. They are going to move along a particular shape. That particular shape is what you call an orbital. So sometimes an electron or a pair of electrons can move in the shape, in a spherical shape. So you call that a S orbital. Sometimes they can move in a dumbbell shape. You call that a P orbital. Sometimes they move in a double dumbbell. You call it a D orbital. Sometimes in a flower shape. You call it an F orbital. So leaving all this, let's come back to our orbitals and our overlap. So you know, orbitals, you always give some charge or you always give some sign, a positive and a negative sign on orbitals. What do the signs denote? What do they stand for? So you know, these signs do not denote any positive or negative charge, because you see these orbitals are places where electrons reside. So they are going to be negative only. But what is the sign actually? For this I would like to invoke the Schrodinger equation. You know, the Schrodinger equation tells you that psi, right? I'll just show you. The Schrodinger equation shows you or tells you there is something called psi, right? So this is like in the form of a trishul or a kind of a symbol. So this psi, he says, is called the wave function of an electron. This can tell you entire thing about an electron. So this is a wave function, and you know, wave functions stand for waves. So here electrons are taken to be as wave natured. So you know, a wave can have a crest and a trough, right? They have ups and lows. As you can draw a curve, you have a middle normal line, and then you have a curve going up and down. So the one that goes upward, you give it a positive sign. The one that goes downward, you give it a negative sign. So that the sign of the wave function is nothing but represented in the orbitals as well, because orbitals stand for the wave function. Okay. So you have given the sign, and there is a rule for overlapping the orbitals. That is, when orbitals overlap, we in turn mean to say that the electrons in them overlap. When I say an S and a P orbital overlaps, I say that the electrons in the S orbital and the electrons in the P orbital are going to overlap. So overlapping of electrons, there is a condition, there is a rule for it. What is it? Very simple. The like signs always have to be overlapped. For instance, I should know that always for an S orbital, I can always give only one sign. It can be, mostly it is taken as positive. Okay, the sign is positive sign. For a P orbital, it is one lobe is positive, the other lobe is negative. For a D orbital, it is like opposite lobes. The cross lobes are same signed, right? And the adjacent lobes are differently signed. It is opposite to that of P orbital. In P orbital, you see opposite lobes are oppositely signed. Here, opposite lobes are likely signed, signed alike, right? If it is positive, this is going to be positive. If this is negative, this is going to be negative. But the adjacents are going to be opposite in sign. So please note these things. This, once you know the way signs are denoted, signs are given to orbitals, you can very well go for orbital overlapping. So you know, there are just two ways in which orbitals can overlap. That is head-head, okay? It's like two people hitting their head on each other, or it's head-head overlap, or sideways overlap. Sideways in the sense, it's like just a partial overlap between two orbitals. So head overlap is going to be more stronger. Let us see how. For example, I first take, I'm going to mix one s orbital and one p orbital. So look how I have mixed. See, this is the only way I can ensure the mixing, because this, let me take this lobe to be positive lobe, this lobe to be negative lobe, and s orbital is going to be positive. Since I said positive and positive can only overlap, here I have my s and one of the p or lobe overlapping on one side. This is only a possible and an effective overlap according to the rules of physics, constructive interference and destructive interference. The same kind of thing is followed here. So when positive and positive sign, when they to overlap, you get a constructive interference. It's going to be a constructive overlap. If positive and negative sign overlaps, it's going to be a negative or a destructive interference. We don't want that to happen. So, and other way, I can keep this sphere in the middle. Keeping it in the middle again would have some negative interference. I don't want that, okay? So this is the only way, the best method to overlap an s and a p orbital. Now coming to p and p. See, coming to p and p, I can have them head-head. This is called head-head. And I forgot to mention one thing. When I have head and head overlapping, I call this bond formed here as sigma bond. Okay? Sigma bond. Head and head everywhere. Remember, head and head overlapping, I get a sigma bond only. Then I see p and p overlapping, and again here it's going to be head. See, the heads of both the lobes are going to overlap, are going to superimpose on each other, provided the signs of the lobes, overlapping lobes, are going to be the same. So here I get head and head. This is also going to be a sigma bond, right? Then come to the next one. I take the same p orbitals and overlap them laterally. So what happens when I overlap them laterally? There is sideways and a very slight overlap happening. This is not going to be effective, though the condition is obeyed. What is the condition? Only plus plus or minus minus can overlap. So now you see this kind of a bond, I call it a pi bond. So what is a pi bond? So pi bond, I can say it's weaker than a sigma bond. It is formed by lateral overlap. Now tell me, which orbitals can involve in lateral overlapping? So those orbitals that are going to have doubly lobed. So it should be either p orbitals or d orbitals, or a combination of p and d. So these orbitals and f, yeah, of course f can also form pi bonding, but let us not talk about them now. So p, d combinations can give you pi bonds. So remember. And look at this, I have shown another pi bond formed between p and d, where the lobes provided. This is going to be, this is going to be positive. So this is positive. If this is positive, this is going to be positive. If this is positive, the adjacent lobe is going to be negative, and this is going to be negative. In p orbital, if this is positive, this is going to be negative. So you see there is a good overlap. So this is feasible. So this, again, I call it a pi bond. Now, what about a case I have not presented here, when I have two s orbitals? So this again is a sigma bond. So usually when you take s orbital overlapping with anything will usually give you a sigma bond. Why? Because anything overlapping with head s orbital is like head on overlap. It's like creating a head on overlap. So hope these things. So with this kind of a knowledge, we are entering into the next phase. Okay, come on. We are now getting into the molecular orbital theory formulated by Hund and Mulliken. So these two people, you would have heard about Mulliken and Hund. Hund's rule we learned. So those people, they came up with this concept of molecular orbitals theory. So why do we need this theory? So this theory was needed to account for many factors which we will be learning when we once construct that particular molecular orbital diagram. Okay, I'll tell you different points. How this molecular orbital theory works. So when a theory is found, when a theory is presented, you have to have some certain postulates. So certain assumptions have to be made, because we do not know exactly how an atom is present or how an electron is present in an atom, and the whereabouts of orbitals are not known to us. So we should have certain postulates. So those postulates I will tell you in simple words, okay? So first, it tells you that just as we have an atomic orbital, in atoms we have an atomic orbital like s orbital, p orbital, d orbital, or sometimes even hybridization doesn't happen in atoms, it happens in molecules. So in atoms you have these individual orbitals. So these orbitals are where electrons can reside in atoms. They are called atomic orbitals. Suppose when you take molecules, molecules are a cluster of atoms together. So in molecules, the electrons present in the entire molecule or in all of the atoms constituting that molecule will be residing in an orbital called a molecular orbital. So how they are formed? Atomic orbitals are combining. So you call that combination as LCAO, linear combination of atomic orbitals. So linearly they combine, you call them. So this is a mathematics approximation method where you linearly combine both the atomic orbitals and you get the molecular orbitals. So how do I do that? Again, by thinking that electrons are waves, electrons have dual property. We take this particular property of electrons, the wave nature of electrons. So every electron, or you can give an electron or an orbital can be represented by the wave function psi. So this is psi b and this is psi a. So let me take the psi b represents an electron, or the psi b represents an orbital, an atomic orbital. So this psi b can overlap with psi a. So it can overlap in two ways. That is, if I take psi a, psi b, psi a are nothing but wave functions that denote an electron wave. For example, this can be a wave and this is another wave. Now two waves, I am going to join them, I am going to combine them. How do I combine? So they can be in phase or out of phase, correct? You just visit some physics concept, how waves can interfere or how waves can combine. You call them destructive interference and constructive interference. That is when two waves are going to interact. Call them the crust of both the waves. If the crust of both the waves are going to overlap, you call it a positive overlapping or a constructive interference. If the crust and the trough are going to overlap, it's a negative interference, right? So please go visit these concepts if you don't understand the basics over here. So my interference or my overlapping can be of two ways. One is constructive, the other one is destructive. So in constructive, my wave becomes powerful, more powerful. It becomes more of a bonding wave. So that is what here you see, both the wave functions can sum up constructively. They can add up, and that I call it as BMO, bonding molecular orbital, because here they are going to combine constructively. This is called constructive interference. So here they are going to give me a stable arrangement, a stable orientation. So this I call the bonding molecular orbital, the stable one, the less in energy. You see, this are three different energy levels. So here my axis is energy. So in energy axis, you see, my atomic orbitals are going to lie at a particular level. If they both combine constructively, their energy is brought down. See, they should have been here, correct? Their energy is brought down by a level. When you call energy is lowered, you call it a state of stability. Similarly here, you see, when they overlap destructively, this is called destructive interference. You call that orbital as antibonding molecular orbital, and so the orbital obtained in that case becomes raised in energy. You call this antibonding. So raised in energy unstable, lowered in energy stable. So any electron put into this lower orbital will be stable, any electron put into the higher orbital will be unstable. So this is the entire thing about the molecular orbitals. Now we shall see how to put our electrons into molecular orbitals and predict the various properties of our molecules. Come on.
Ask the atoms.